The lore of physics has it that, in 1589, Galileo dropped different masses from the Leaning Tower of Pisa to demonstrate that all objects, regardless of their constitution, accelerate at the same rate towards the Earth. An experiment which would help inspire Newton's laws of gravity. That this interpretation was wrong. Indeed, if Newton and the theorists of his era had looked a little more deeply into their own laws, they might have realized that it was Galileo, the Tower of Pisa, and the ground that were accelerating up all along. As it is written in his Principia Naturalis, Newton's first law states that every body perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereupon. Ordinary intuition from our everyday experience tells us that things fall down. Apples, water, sometimes people. But sometimes ordinary intuition is a pretty bad guide, and it can take a little deeper reasoning to sort the truth out. An operative definition to the concept of motion. Specifically, acceleration. Indeed, not long after developing special relativity, Einstein himself considered this question, in the context of asking whether a man falling off a building could measure his own weight. Well, it turns out there are a number of operative definitions you can give to accelerated motion. And indeed, you can apply them right here at the surface of the Earth. But only if you're ready to accept their astounding implications. Now, if you're familiar with general relativity at all, you know there's another kind of statement we can make about being in an accelerating rocket ship. We can claim that we perceive ourselves to be in the presence of a homogeneous gravitational field. This is the equivalence principle. By flipping it around, we can also claim that any frame in which we perceive a gravitational field can likewise be treated as accelerating. Meaning we can make the same funny assertion about being in a gravitational field that we did about being in an accelerating rocket ship. That is, we can say that space itself is flowing past us, getting sucked no longer into the floor, but rather into the mass or source of the field. Now, the primary place we perceive a gravitational field is at the surface of the Earth. Okay, but this is just a clever analogy. Space isn't really flowing into the Earth, is it? Well, now comes the incredible fact that you aren't actually at rest on the surface of the Earth. The ground is, in fact, accelerating you upwards at 9.8 meters per second squared through space. A velocity of approximately 11,000 meters per second. In classical physics, this value is known as our planet's escape velocity. It's the velocity at which you are traveling through space. Indeed, your continual acceleration of 9.8 meters per second squared at the surface of the Earth, ensures that you are always traveling at this velocity. Always traveling at this velocity. If you drop an object off of yourself, it falls to the ground for the same reason it did in the accelerating rocket ship. Because the ground rushed up to meet it. If you're skeptical of this fact, you can prove it to yourself by stepping off of a tall building. We said by stepping off of a tall building. There we go. Now, this action will cause the gravitational field in your immediate vicinity to vanish before any light signal has a chance to reach it. This is a violation of causality. This fact, in conjunction with an empirical inability to measure the field you are supposedly falling in, forces you to conclude that the field you perceived the moment before you stepped off the building was indeed a fictitious one. And that implies that it must be the ground which is accelerating, not you. But this incredible fact immediately raises a whole host of other questions. How can one part of the Earth's surface be accelerating upwards, while miles away another part is also accelerating upwards, but in a slightly different direction? And meanwhile, at the antipodal end of the planet, that same surface is somehow accelerating in the completely opposite direction. It becomes even more mind-boggling when you realize that, even though the Earth is hurtling apart in every direction, it somehow remains stationary with respect to itself, even though there is no force acting to pull it together. How can one part of the Earth's surface be accelerating upwards, while miles away another part is also accelerating upwards, but in a slightly different direction? And meanwhile, at the antipodal end of the planet, that same surface is somehow accelerating in the completely opposite direction. To answer the question of how we can all be accelerating and yet all remain in place, let's imagine a large flat basin of water. Of course, in this visual, the basin is relatively small